Now, there is a standard way for eliminating the constants in an equation like this. And that standard way of doing that is something called working in natural units. Every problem has a certain set of units, not necessarily, meters and kilograms, but a certain set of units that are natural to that problem that make the problem much simpler. The other term for this is something called dimensional analysis. And the idea goes as follows, right? When I look at these equations, if I wanted them to line up perfectly, I just need to get these constants to go away. So I would really love to be able to replace h bar squared divided by m with 1. And I'd also like to replace m omega squared with 1. Because if those were equal to 1, then when I cross them out here of my equation, right? Cross them out carefully. Then notice I just have 1/2 of 2 derivatives plus 1/2 of x squared. And the other Hamiltonian is 1/2 minus 1/2 again of 2 derivatives plus 1/2 of the variable squared. So these Hamiltonians would then be equivalent to each other. Now, you can't, though, just set a combination of constants equal to 1. When I was a student, this maneuver really always bothered me because it's not 1, it still has units on it. So what happens to the units when you do that? The way I finally found to think about this that made me much more comfortable with the concept, and I'd like to share that with you now, is to carry out the analysis in the following way. Right? If I look at this h bar squared divided by m that I just crossed out, notice when I then divide whatever its units are by meters squared, right? Because multiplying by a derivative, you're multiplying by 1 over dx squared, right? So this thing, h bar squared on m, divided by meters squared, gives me something with units of the Hamiltonian or units of energy. Right? So h bar squared on m divided by meters squared has units of joules squared. So h bar squared on m really, in standard units, has units of joule meters squared. So if I'm going to find some new system of units, right, where the value of this thing just happens to be 1, it's really not just 1, right? It's 1, but it has units associated with it. Are our new units. In particular, it would be 1 unit energy, unit length squared. To parallel what we have in standard units, just I'm calling my new unit of energy instead of a joule, I'm calling it a UE, a unit energy. And likewise, my meter, instead of calling it a meter, that length, I'm calling it a UL, a unit length. M omega squared has a similar issue with it, right? It has units because when I multiply that one by x squared, I get something with units of energy. So its units must be joules per meter squared. So this one would have natural units of joules per meter squared in standard units, And in natural units, it's going to be 1, numerically speaking, but it's going to be 1 unit energy per unit length squared. Now, this is sort of my design criteria for my new system of units. Our job now is to engineer the unit energy and the unit length so that these have numerical value equal to 1. And we can find those values simply by solving these equations for the unit energy and the unit length. So to solve these equations, let's call this first one equation 1, and let's call this next equation equation 2, and then we can do some math with them. So for example, if I take equation 1 and I divide it by equation 2, that will turn out very naturally for me because on the right-hand side, if I divided these two things, the unit energies will cancel and I will be left with 1 unit length then to the 4th power, right? Now on the left-hand side, when I divide these, I get h bar squared divided by m divided by another m. So that's going to be h bar squared divided by m squared. And there's also, when I divide it by equation 2, an omega squared in the denominator. So this tells me the value of 1 unit length to the 4th. So I can pretty quickly solve then for 1 unit length, would be the fourth root then of this quantity here. And the fourth root of that, well, the square root would give me h bar on m omega, but I need another square root. So then this would be to the power of 1/4, like so. Now, one little side note, something that confuses students a little bit is, well, it looks like the u's, though, are coming, you don't want to say when I do this division that I get a u squared L to the fourth or something like that, right? The UL is one unit. It's 1 unit energy. It's like 1 millimeter or 1 kilogram, right? When we square kilograms, you don't get a kilogram squared, you get a kilogram squared. Okay, now, my unit length, it's nice to give this a variable name. I'm going to call this x naught. So anytime I get a distance that's equal to 3 in my natural units, in real units, it's really going to be 3 x naughts. It's nice just to double check our analysis here. We can verify that we indeed have the correct units on this x naught. So let's just do a quick verification here. I don't want to use up too much of my space up above. But the Planck's constant, remember, has units of joule seconds, which would be kilograms meters squared per second. And then that has to be divided by then, I'm sorry, this is clearly to the 1/2 power. I overdid it, right? When I took the fourth root, the square root part got rid of the squares, but then I had another square root to go. So this should have been 1/2. So it's good we're checking the units. So the h bar is kilogram meter squared per second. Then I divide by m, which would be in kilograms. Omega would be inverse seconds. And notice then when I look at these, the kilograms will cancel, the inverse seconds cancel, meter squared to the 1/2 would just have units of meters. So indeed, the units come out properly. Great. So now we know the unit length. For the unit energy, I can do something very similar, right? Clearly, if I multiply these two together, the unit lengths then will cancel. So if I do number 1 times number 2, on the right-hand side, I will get, as we were just saying, unit energy squared. So this will be 1 unit energy squared. When I multiply the left-hand sides together, I get h squared on m times m omega squared. So interestingly, the m's cancel, and I'm left with h bar squared omega squared. Oh, that's pretty. That's very nice. So then 1 unit energy is actually equal to, I just take the square root of this, h bar times omega. Oh, now that sounds very familiar. We're going to come back to that in a second. Just a few triple checks first. Notice I might want to give this a name. I might call it epsilon naught, my basic unit energy. You can check the units very quickly. Remember that h bar has units of joule seconds, whereas omega has units of inverse seconds. So this thing will definitely check out to have units of joules. So that's good. And what has me so excited here is notice it's saying h bar omega is my basic unit of energy. And what's very intriguing here is that if we look at the Bohr-Sommerfeld quantization condition, in traditional units, the energies are, h bar omega, 2 h bar omegas, 3 h bar omegas. But since h bar omega is our natural unit of energy, when we work in natural units, my energies will come out just to be 1, 2, 3, 4, etc. So it really does seem that the natural unit of energy for this problem should be h bar omega, and in fact that's what this dimensional analysis here is really telling us. So now, we are now going to work in these natural units throughout the rest of our analysis and the rest of our lecture. And once we've decided to do that, then indeed the values that I've crossed out here were all just ones. And you will notice then that the Hamiltonian looks exactly the same whether I'm in the position representation or the momentum representation.